let's do another example. So in example number 5, it asks, in the game Scrabble, a player pulls the following 7 letters, A, F, H, M, N, T, U. How many different 4-letter arrangements could be made? How many different 7-letter arrangements could be made? And we want to know what to do. Well, first of all, there are no repetitions, and since there are no that's kind of important. If there were repeated letters, you got to be a little careful because it would actually change a little bit, and we'll get to that later. But if each choice is unique, we could again use the fundamental counting principle. Let's say my first choice, I have 7 letters. Like if I'm imagining having the little tiles, I'm starting with 7 choices, so I could put one first. Then the next choice I have 6 and 5 and 4. So the number of 4-letter arrangements should just be 7 times 6 times 5 times 4. But additionally, this is the same thing as a permutation because I'm trying to figure out how many arrangements there are. And those sort of words usually are a trigger to imply that permutations. And since I have 7 objects to start with and I'm trying to pick 4, sometimes people call this 7 pick 4 instead of permutation. Like that's another phrase that I've heard people say. But basically, this is going to be 7p4, 7 pick 4. And sometimes for combinations, people say 7 choose 4. But, this would just be a permutation of 4 objects taken from 7. And again, I could remember how to do that in various ways as 7 factorial. Also remember, it's not just 7 factorial divided by the bottom. It's it's the first number factorial divided by the difference on bottom. Or, you could memorize that as that's 7 times 6 times 5 times 4. That I need 4 numbers in the chain because there's 4 selections based on the fundamental counting principle. And as I select one, it gets lower. So the point is there's a lot of different concepts and they're all kind of similar. Ultimately, that would give us the number of 4-letter arrangements. Now, another thing you might be wondering is how many of those will be actually words? Because if I just take 4 letters at random, like M-A-T-H, oh, that's an accident. Not really. That's an actual word. But say, for example, I take T-U-H n, right? That's not a word. So if we wanted to know how many words there are, that's a whole different question, which you'd have to compare to an event space which had all of the 4-letter words of those, as a predefined notion. And that's how a lot of those computer calculators work for, if you've ever seen, solving all the different Scrabble words you can generate from these letters. It's fairly easy to program. You just need to really just have a dictionary of all the legal words at your disposal for cross comparison, if you're trying to write a computer program to do that at least. But anyways, if we're just thinking about arrangements where it can be total nonsense, unlike the actual game Scrabble where you can't make words with nonsense, unless you're my mom and she loves to make fake words just for fun. But anyways, that would be 7 times 6 times 5 times 4. That makes 840 unique 4-letter arrangements. And so this is why the game is difficult, right? If I'm trying to build words, there's so many different options that, we can't necessarily run through them all as we're trying to play the game. And there's a lot of different strategy for doing it. Or let's say I wanted to do how many different 7-letter arrangements would there be? That would be 7 pick 7. Basically, I'm going to try to make a full 7-letter word out of that. And that would be 7 factorial divided by 0 factorial. Because remember, it's always the first factorial divided by the difference factorial. And this actually brings up an important point is, well, what is 0 factorial? Because you would think that 0 factorial is 0. Because, right, we always start at the number and use a multiplicative chain. But it's sort of like why, we talked about this in class a month or two ago, is like why is something to the 0 power 1? Actually, 0 factorial is defined to be 1. And this is just another definition. It's because factorials are in the multiplicative universe. They're in the universe of multiplication, and you never start at 0. So the starting point for factorial is 1, not 0. It's just it's a necessity of the system, and there's a lot of mathematical reasons why that needs to be true. I know it kind of doesn't make sense based on the pattern of factorial. And actually, another thing that's kind of interesting is there's such a thing as having like a fractional factorial, but again, it's we're not going to get into that. There's different contexts and meanings and reasons why those things would need to happen. But anyways, that's just going to be 7 factorial. Or kind of as if we're doing a complete chain of all of them, it's always just going to be, well, how many letters there are, factorial. And I think the book says this somewhere, is that if you're going to permute all n objects, it's just n factorial, which is kind of easy to remember. It's because it's going to be, well, my first choice, I have 7 letters, then 6, then 5, then 4, then 3, then 2. And then by the time I've done all that, the last letter is, there's no choice. There is just going to be 1. And anyways, the number of 7 factorial, obviously I could just type out 7 times 6 times 5 times 4 times 3 times 2 times 1 in my calculator, but it's easier just to use the factorial key. And there would be 5,040 unique arrangements of those letters. Again, where order matters. If order did not matter, then it's a whole different question. And that's what we're gonna get into next is combinations. What happens if I'm taking selections and the order of which I'm taking them does not matter? Then it's a little bit different. Anyways, see you in the next one.